Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with learnbay.co. Happy learning!
Okay. So, what is reinforcement learning? Okay, so reinforcement learning is a branch of machine learning that permits system to learn from their outcomes of their decisions. Very, very important. So, I am saying that reinforcement learning helps the machine to learn from their outcomes. We are not using any data. That's a huge difference between a machine learning, a deep learning, and a reinforced learning. I will not require data. So what I will do is that I will have some random choices. Machine will take some random choices and refine its thoughts based on the actions it takes, like a humans. It is trying to mimic the thinking of the human brains. So what we are doing, there are four important things we are doing. We are computationally approach of learning from actions. We take some actions and see whether that action is correct on that environment. So what is the environment? So for us, a real environment is maybe you are sitting right now, right, in a house. You are attending a reinforcement learning session in Learnbay in your own laptop. Maybe you are sitting in a house. That room is environment. Okay, now suddenly you think that your pet dog comes up and you're trying to learn it. So what you will do, you close the door, right? That is the action, right? The action you take on the basis of the environment. And those actions are based on your past experience. Okay? Learning through trials and error. Okay, that's a very, very important thing. So for example, learning through trials and error means, so so in the chat, when during the like 10 to 12, 10, during after 10 you were learning calculus, right? Calculus, or preferably us like differentiation or integration. We learned, so previously it was tough, right? With practice and all, we are able to get better through it, right? Maybe trials and errors can be very much interactions about when people are investing first in the stock market, right? So you just hear something in for example, in money control, and you buy a share, right? That's a trial and error. Then you make a mistake and refine yourself, right? So that can be a trial and error. Learn by experience. It's a very, very important thing. So for example, in certain certain professors in the college, right? So when that professor used to take our class, maybe first for the first 4 or 5 class, we are not able to understand, right? Then what we'll do is that then from our experience we know that we have to consult somebody in our class that are very good, right? Or maybe we take a help of an external book or maybe some online sessions to make our concept clear. And goal oriented learning, so we have a goal. Actually every time in our life also we have a goal. So what can be your goal? My goal is to get a good job, maybe increase my salary to 30% next year. That is a goal. My goal is to learn, acquire knowledge, right? My goal is to lead a better life. My goal is to stay healthy during COVID, right? These are the goals. So machine will also have some goals, and it will take actions based on that goals. It will learn the experience and refine the actions. So I will just have a drawing on this.
I have a question, sorry to interrupt.
Yeah, yeah.
Yeah. My question is, like you said, right? It will be random move first. Whenever that you try to learn something, right? In case of reinforcement learning, right? But if you see generally, whenever we are learning some things, right? Suppose you take an example, like you're trying to sum. Okay, we have a prior knowledge of numbers first. Then our teacher will give some one or two example. Okay, this is the way sum is happening, right? So it is not like always random, right? So somebody taught us, okay, these are the numbers, and this is the example, one or two examples they gave. Then we go for further then. So how it is always like random, you can say, like.
Yes, good question. So there are a couple of answers to this. I will try to try to give answer in different dimensions. Okay. We will see that there are couple of branches of reinforcement learning which deal with different things. Okay. So I am saying about numbers, right? Random, but there is a different meaning to it. So there I will go a little bit of deeper. Okay. We have what type of learning we do in machine learning. Okay, take example of machine learning. Okay. We learn from data. Okay. So in certain cases, we don't have data. What you do? So you are saying, example, you are doing a linear regression. Okay, predicting sales. Okay, your sales is a Y, and maybe you have some input variable, maybe temperature. So I am predicting sales based on function of temperature. You, for example, you have very less sales data, maybe 100. How will you approach this problem? Machine learning cannot be done with 100 data. Maybe not 100, maybe 20. You know that, right? Less than 30 data, you cannot do any machine learning. Why? Because our central limit theorem says that you require 30 samples to do the like you require minimum 30 samples to do a central limit theorem. So less than 30 samples, it will not fall into a normal distribution. So how will you solve this problem? So here what we do a Bayesian kind of thing, right? Bayesian statistics, right? So we, from our previous experience, we know that what is a distribution of sales. So we say that it's a gamma distribution, right? Or a beta distribution. And then instead of relying solely on data, we start with some distribution based on our from our previous knowledge, and try to refine the sales. That can be one approach that we take in machine learning. Okay. Next, deep learning. Okay. So deep learning, how the weights are initialized. I randomly initialize the weights, right? I am not, so you will say why we are doing it. I have to start, right? So there should be a starting point. I try with a random weight, zero weight, random weight. Then I have activation functions, right? Then I have a loss functions, right? Then based on that, I refine the weights. So I start with zero. Maybe I am used a loss function like a log loss. I want the log loss to be very close to zero. With that function, I start with zero and refine the weights. I start with 0 weight. At the end of deep learning, my weights are 0.1, 0.2, and 0.3. Think of reinforced learning as such. You do not have a starting point. So what is the problem? I start with zero. I learn from my experience and incrementally refine that experience. From that zero, I learn, and maybe the end of the my learning, I change from zero to maybe 0.1. So here we have a function, but reinforcement, we have a function like a log loss. Reinforcement learning doesn't have a functions. It doesn't have anything. It takes a decision and learns from it. So that we will see how it does it. But what is the problem with starting with zero, right? Random numbers. It's from zero random numbers. But based on our experience, maybe after 5,000 iterations, I get better at that. For example, we are humans, right? You do not know about share market at all. So you start with some random shares. You buy it, make loss. What you will do next, you go to that company and read the annual statement, read the investor reports, and then you invest. Then you get better at it. Or maybe you read some books of stock market and think that what are the top 20 markets that are driving Nifty, right? You buy those stocks only. So we also do it always. So when you do not have anything to start on, we start with a random thing, right? So this, or start with 0. So this is a point I wanted to highlight, that when you have nothing, you start with 0 or random, then we'll refine our thing based on our experience. Is it clear?
I have some question, but anyway, okay, fine. I'll take it.
Okay, so here what we are doing it is, we are, for example, there is a environment, right? So we'll see, there is an environment. We take some actions based on our environment. We take some actions, okay? Then we will see, when we take some actions here, and then what we will do is that we will, so there is an environment, sorry. So what I do is that there is an environment. On that environment, I take some actions. So I will get some result. Based on the result, I again refine my actions. So I'm talking about this part. So we'll get it clear. Okay. So maybe in later slide you will see. But a sort of this. So we are taking some actions. We are getting some result. Maybe action 1, and we refine our action 2. And then again it goes in a very, very cyclic. And this happens in a bounded box. So this happens, the entire thing, sorry. So this drawing would be, this would be an environment. I have a starting point. So we'll start with 1. State, we take action. We move up into the next state. We take another actions and come back. Based on that, whether the action was successful or not. You can think of this as a starting point. Okay. Next part is next part is what I will show you some of the examples where the reinforcement learning is practically used. So, for example, if you think about so, for example, these are the papers you can learn that how the reinforcement learning is been done. So here you can do is that you can see this one. I think this link is Deep Minds. So see here how they are using machine. Here they are using this. So see, this is a use of machine. See, I am training the robot to climb it. So do you think there is any input to it? So with the obstacle, the robots is trying to learn things. It is trying to clear the obstacles. This is one of the use case for reinforcement learning. So you have to train the robots to clear the obstacles. Next thing is that there can be another way. I am trying that robot to jump, right? Jump. So there are these are the gaps. So the robots is able to jump based on reinforcement learning. So here you do not have data, right? So I have to start from some point and able to train the robot. Maybe the robot will like fall down in couple of instances, but it is able to learn with more episodes. So we'll explain that. So see, this is another instances where the robot is jumping. So these type of cases, we are using a reinforcement learning. So it's not about jumping, it is able to help robots to walk. Help the robots to walk. This is also let the robot to see, the robot is doing some activity, right? It is falling into the store, this and this. So everything you can mimic with the help of reinforcement learning. learning. So a lot of applications of reinforcement learning is in robotics. Okay, so this is a first instances. This is a very good story that you have heard, that AlphaGo, right? So AlphaGo is one of the complicated games. It is a most complicated game to play. It is kind of a Chinese game. So see it through reinforcement learning, it is able to like in 3 days, it is able to beat the world champion, that guy. So it is able to beat the world champion Kijia in just 3 games in 2017. You have trained the model. So, and it is very complex. So if you think about AlphaGo, it is very complex. It's like a Chinese checker. It's like a chess, but it can have infinite moves. But the machine is able to learn that through reinforcement learning. So this type of applications you will see, this is a real AI we are talking about. So this is the artificial intelligence, what we expect that the entire field to go in the next 5 to 10 years. This is a real artificial intelligence, what we have dreamed of. Okay. So you can read about, maybe I will touch upon the self-driving cars. So also you can use a self-driving cars reinforcement learning to learn about the self-driving cars. So self-driving cars uses a lot of reinforcement learning. So you can read about it. I will not go deep into, but again, so reinforcement learning, why it is used? Because self-driven car, you have some obstacles, right? So pedestrian comes, you cannot just like kill him, right? So you have to decrease the speed as well as go left. So if there is a car in front of you, so it has to learn from the real learning. So learn from the obstacle and refine its learning and move. Okay. So you can read about this. So this talks about an entire sets of use cases that you can do for reinforcement learning. So I have given this one. It's a very simple, is that a child learns to ride a bicycle. Okay, so you are an agent and this is an environment. And when, so for example, you have a little child. So he's trying to learn it, right? So you bought a bicycle for him. So you will tell that if you are able to ride that bicycle from here to the gate, I will give you chocolates. So what it will happen, the bike will, the child will try to run it. Okay, to the juice stall preferably. So in 2 or 3 instances, when the first day it will fall down, right? Maybe second day it is what, so the distance is preferably 1 kilometer. So it goes around 500 meter and falls down. In third day, it goes around 800 meter and fall down, right? In maybe in a week, it is able to at least learn from that. So this is a thing what we're talking about. So the agent and the environment and the rewards. So agent is what? The child is agent. Environment is the road. And the reward is that maybe some chocolates or juice you are giving. So that's a kind of a practical applications of, so reinforcement learning actually mimics what we humans do. So this is one of the case of a practical experience of reinforcement learning. Second is that maybe a child falls due to hurdle or on the way it gets hurt, right? So I talked about first day, it is not able to control. Maybe there is a steep slope or maybe there is a hurdle, right? So when he falls down, you have to give him a negative rewards. Maybe we do a kind of a beating to him and say that you are not able to ride it. Okay. So these type of agent should also be given a negative and a positive reward to refine its action. So if you only give positive rewards, then it will not able to learn, right? So with each action it takes, it wants to give a negative reward. So maybe he's riding too fast. Okay, there can be a negative. So you tell him to slow it down, right? Or maybe it is like he is not able to balance himself, right? Then you have an extra 2 wheels in the bicycle, right? That will help him to balance. That can be one of the ways, right? Or you do is that maybe he's falling down. Maybe you decrease the length of the seat, right? So this is also there will be a negative rewards and a positive rewards. Okay. Similarly with chess, right? So chess, what you do is that there is an agent and there is an environment. So this 8x8 block is the environment. Okay. And you make one move and the other guy wants make another move. So what is the reward? is that maybe if you win the chess, you will get some cash discount, like maybe you will get a prize. So prize is a reward, and your environment is a chessboard, and your agent is you who is playing the chess. So this can be a practical example of reinforcement learning. Third thing is that so a chess player loses his game, right? It gets disappointed and gets a negative reward. So maybe you make a move, right? And you try to, so how we learn chess, right? So you lose around 10 games from a very strong player and you understand the move, right? And then you get better at it. So that's a, each of the game you lose, there is a negative reward associated with that. And we learn from it. So
One question.
yeah.
Sorry to interrupt. One question.
Yeah.
So, okay, take example of chessboard.
Yeah.
Whenever you play chessboard, okay, so we either win or lose. But whenever you win, you said like, okay, there will be a reward if they will get right. Okay, so this is the way if they play, then they can win, right? But the thing is that here the moves are like it will remember, right? Like, okay, these are the moves if I play, then I may win the match.
Yeah.
But there is no like suppose it will do a move, there is no reward after that. So after the winning game only they'll know that okay, this is the like the correct move we are doing. Is not it? It's trying to remember the moves also. Like okay, this is the
Yeah.
if this is
So
the way I play,
tell me
I'll win
from
the
your
match.
experience, you are a
Yeah.
better chess player, right? Do
Yeah.
you always remember that what you did maybe 2 months before? Actually, it starts with our instinct, right? So we are not in our brain, we have that, but still we know from that opponent's action that what next move will be. We are not remembering that maybe like 3 months before, because of that move, I have given that move. So it is not at all that we need to remember, but if what reinforcement learning does is that maybe it mimics the environment. So what it does is that it, for example, for a machine, if you put rules, it is not reinforcement. Again, I tell you. So chessboard, I have rules, right? I can use that rules around maybe 1 lakh of rules I put around in that, like in the algorithms, and I will give a reward. And then what will happen is that if one of the moves, so if what it does is that you make one move, your opposition moves does the second move. So now the algorithm says that maybe if the like opposition gives the second move like this way, my move. So for example, think of these terms. This chess game can be a machine learning as well as reinforcement learning. Okay? So how machine learning? So this is you, right? This is player 1 and player 2. You are remembering. So it's a machine learning, simple as that. You have rules. So you build a tree, for example. So you say king, that is opposition move. Okay, when I move a king, the opposition move, I move a horse. It's my move. Okay, I move a horse. I move like a elephant. I win. So you are storing this. It is your move, and your opponent's move is maybe he moves a boat, and then he moves a pawn. You win. So you store these rules, thousands of rules, and then when your opposition just takes one move, you just see the branch of your tree, or you will say that player 1 move 1 into move 2, then you move 3, I win. So this is based on rules. This is not reinforcement learning. This is totally machine learning. Okay, these are the well remembering. Reinforcement learning will not do those things again. I don't care. So what I do is that what the machine does is that machine does one move, an action. Okay? Sets of actions. So from move 1, action 1, reward 1. Okay, it moves into the next state, move 2, action 2, and reward 2. Maybe it does around 1 lakh of times, and then it will be maybe he's winning or losing, right? So based on that, what it does is that it have an intuitions, okay, among yourself. So what it does is that they are business rules, but it is based on actions, right? So maybe he has seen the rules from the opponents, right? So it has, you know, that based on my experience, so maybe you can think of this grid world, okay? So maybe 4 by 4, it knows that if the opponent gives this one, I cannot take this path. This path is, I'm getting less rewards. I will not do this path. If he moves this one, my best path would be go to the left and go to the right. This move is the best one because it has fetched me higher rewards. So it does in that way. So it is not clearly business rules. So it learns from the environment. Maybe playing 10,000 times and losing, it knows that what will be the best path. So now whatever actions that like opponent give, it is able to do. Okay, that's why when it learns, it is around 70-90% sure that it is able to do. Okay, because it is learning from the experience. It is not plainly or vanilla type rules are there, and there is no data, right? There is no data. So in this type, when you use reinforcement learning, there is a ground rule. There is no data for it. When there is a data, why should I use machine reinforcement? I will use machine learning, right? When you do not have data and the environment is not clear, so this chess is a very simple. It is just for your experience. Nobody uses chess for reinforcement learning. Very complicated thing. AlphaGo, or you're training your robots to work, right? The environment is not clear. The rules are not defined, right? How will you approach that type of unstructured problem through reinforcement? Clear?
Yeah, so regarding that, say robot, we try
Yeah.
to pass the hurdle, right? In that case, is not it like depend upon the height? We know that we will find out the height of a like hurdle
Yeah.
height.
I will just give you the just park that question. So there is one like slide. I will explain you that how a robot is trained. Actually, just park that question.
Okay, that's okay. That's okay.
Just
But
learn that there
yeah,
is some like competing things. So I will just, for example, there is equation y. Y is training the robots to learn. Training the robots to learn. Y. Training the robots to run. Okay. Or yeah. So here can be, its function can be 12.5 of velocity. Okay. V1 means the velocity I'm running. 0.1 of the obstacle. So obstacle is O1. Okay. Then maybe you are 4.5 of acceleration. Then you have some time. So for example, 20 T1. So if 20 for 1 or 5 minutes the robot runs, you think that it is failed. Now with these equations that you have built from your experience, you will try to optimize it and make the robot run. So I will explain you that part, like how will you able to do that. Okay, so just park that questions as of now. So there is some equations and there are some competing the competing variables, and based on that we will able to optimize it. Just park that questions, I will explain you. But this is not a equation that has developed from the data. This is from my experience. That's a major difference between reinforcement learning and any machine. I don't have data. I will train the robot maybe 5 lakh times, and then from there it is able to learn from the environment. It will fall down first, maybe for the first 200 iteration, one step it does and it is not able to check. Then I go inside it, I change the limb of that robot, I change the way it talks. Maybe I will get a different leg, and then it will again, I will be able to help the robot. Yeah.
okay. So one question is like you said, right? You try to uh, teaching a kid to drive a bicycle, right?
Yeah.
So in that case also, what I feel is that you also need to understand that what is your obstacle. Like you require DL to recognize the object, to recognize the track also. So
Yeah.
how that will help like reinforcement learning will have to
Yeah,
recognize
so
the
that's
objects.
a, So that's a, your point is valid. Reinforcement these are advanced reinforcement learning. Reinforcement learning is in the industry currently done through deep learning. So it is known as deep reinforcement learning. So you have the images, you have the video cameras and everything installed. So through like a image recognition or object recognition, like for example, YOLO, it is able to detect the weight, breadth, distance, and then take a decision. So in real industry, we use reinforcement learning through deep learning. So it is known as deep reinforcement learning. So you have the DQN and everything. So every, like for example, like every case, for example, self-driven cars. So say self-driven car uses a object detection, right? But with only deep learning, it is able to detect the height, weight, like obstacles and all. But what actions it will take, reinforcement learning will take. So it's a combination of reinforcement learning plus DL. It is known as deep reinforcement learning.
You mean it's like decision making power will give it to reinforcement
Yeah,
learning?
but this is advanced. So we will not covering this, but the concept remains same. But we have to understand this one pretty well so that we can understand this one. So it is reinforcement learning through deep. So you have equation, for example, y equal to fx. So this, consider this to be a reinforcement learning. Consider this. I can solve through normal any algorithms, or I can solve through an activation function on deep learning. So this is deep reinforcement learning, but the concept remains same. Actually, this is a equation. I have to solve it. I can solve through anything, right? So that might be a deep learning, or that might be a reinforcement learning. You can use, maybe I can use a Excel solver to solve that. So this equation would be given by reinforcement learning, but how you solve it, but totally in the industry, it is solved through deep learning. So that's why it is known as deep reinforcement learning. So for example, you can use a Q learning. So I will explain to solve this equation. So if I use a deep learning or a deep learning with that, then it becomes a deep Q learning. That's a difference. Okay. So somebody was asking some questions.
Just a question. How is reinforcement learning different from cognitive computing?
Cognitive computing is, I think, a broader term. So cognitive computing, there are many things that can come through cognitive computing. So reinforcement learning, you can think of is a part of cognitive thing. Cognitive learning is so reinforcement learning is a big, so reinforcement learning is the like the robots or the agent is thinking and taking the decision and refining the learning. But cognitive thinking is something that a part of reinforcement learning where a robot is not learning from the data but learning from the experience. But whatever actions, rewards, and then refining its decision is reinforcement learning. In reinforcement learning, we use cognitive thinking. That you can think. So reinforcement learning is a broader umbrella, and
Okay.
cognitive thinking is a part of it. Okay. So yeah.
One question. How system will come to know which is the positive outcome and which is the negative outcome, because
Very good.
or
Good
either
question.
we need to program it what
Yeah.
desired outcome we want.
Very good question. So we will see. That's a major problem with reinforcement learning. Reinforcement learning, you have to design your reward function. Okay, nobody will tell you what. So that's why this PhD data scientist and domain expert who are working for this industry for a long time, they design the reward functions. Because you will not able to understand, right? That's a main hindrance why reinforcement learning is not scaled up. So every reward function you have to design based either on your experience or like based on a conceptual understanding. Okay. Or there can be another way that I try to there is a like sample or subsample given from maybe a 10 records, and then I will use some concept like a dynamic programming to get close to it through sampling. But the reward function you have to define. That's a major problem. People are not able to define their reward function. For simple task, you know that. Then you have to do it by experience. So you take around maybe for the 1 year or 2 year, you're observing the robots and taking all the observations, and then you are defining your reward function and then passing it into the learning. Maybe that is not optimal. Then you have to refine your reward function and then again you can apply it. That's the main hindrance to the reinforcement learning steps.
So time by time, human intervention is required.
Yes,
You mean
yes,
to
yes.
change.
Yeah, how will you then? You have to define your rewards function, right? That's a very complex thing. Okay, so what is the crux? The agent is somehow who takes action. Agent is moved. Agent is a move made by the action is a move made by the agent. Environment is a world through which the agent moves. State is a situation in which the agent finds it itself. And a reward is a feedback in which a success or failure is made. So these will come a lot of times. What is agent, what is action, what is environment, what is state, and what is reward. So these are very agent is I am agent. Okay. Action, agent is your kid is agent, for example. Action is he is riding a bicycle. Environment is the road. State is the situation. So maybe like he is able to go to the gate from your for example from the door of the house to the gate. So that is a gate is the final state, and the initial state is the door of the house, and the reward is maybe we'll give him a kind of chocolates if he can go from your gate to the gate. So that is the entire terminology we'll be using. Okay, so reinforcement learning applications. Okay, the reinforcement learning applications can be to manufacturing, games, media, business, healthcare, and finance. So there is a lot of applications, but still it is evolving. It is evolving means in next 5 years, you will see that a democratization of reinforcement learning that you see in deep learning. So why? Give me a question. Why do you think that the deep learning has kicked off? Before 2015, deep learning was not that people were struggling with it. Why do you think the deep learning is right now democratized and people are very like people are using a child can like use a deep learning to preferably do task. Before that, it was a kind of a PhD paper, right? Why do you think the deep learning is democratized and people are right now easily using deep learning? Why?
It's because there is zero feature engineering you have to do, and second is it's universal approximation. So you don't require any like engineering approximation function.
No, but there is a
Automatically.
fundamental difference that has occurred. Can anybody tell? I don't know who has taken the class of deep learning. So maybe in deep learning, what was the main hindrance? Before 2015, you know that about ImageNet problem, like that Jeffrey Hinton solved. Okay, FaceNet problem, he was able to detect face. So it took around 2 to 3 months to run it. Hardware.
Computation.
NVIDIA has transformed the entire landscape, right? How? Because you have better hardware. So batch normalization. Now you can have a machine of preferably around 64 GB, 128 GB with GPU CUDA to load those images right in a batch normalization. You are able to load multiple images run your batch and get that output. So for example, the loss function, it is very quick. Previously, and epoch used to take around 1 day to run. Right now, you can take around 2 minutes to run epoch. You know that, right? Epoch is number of times I am scanning through the entire images. And what is batch? Batch is the number of images I load into my GPU, right? 64 is nothing. NVIDIA is coming up with 312 GB. So how many images you can think of? So that's why it has democratized, because of the hardware. So this reinforcement learning, the major problem is the hardware, and the next thing is that it's still in research. So no company has come up with hardware or software to democratize it, right? You know about GPT-3, right? NLP has been democratized. If you don't know, just search. GPT-3 is transforming the entire landscape. So you can just write fetch data from two tables. It will run a SQL query on the back. You will say image detection cat and dog. So it will run the code. It will just convert that your English language to the code and run a CNN to extract the images. So companies or institution democratized it, and reinforcement learning would be democratized, but it is main hindrance is the hardware, and people are not investing it. Why people are not investing it? Because there are no stronger use cases. Deep learning was democratized because of NVIDIA. Why? Because of vision. Vision, because of lot of use case in vision, NVIDIA has democratized deep learning. So deep learning has clicked in because of that vision. There are a lot of use cases in vision. So we require some strong use case for reinforcement learning so that the NVIDIA will invest in making a better hardware and a software. Maybe you will require just an API to run it. Maybe you don't know. Okay. So challenge in implementation of reinforcement learning. So one is that time and computational power. That's a major hindrance. So if you think about computation power, you have to train the robots maybe for 1 year to get the result, because there is no data, right? It will take some from the environment, it will take some action, it will get some reward, and then it will refine its action, right? So we'll have to run it for maybe 2 years. So do we have a computational power to do that? We don't have it still. Domain. So next thing is that in order to implement any such technology, you should have a domain agnostic thing, right? So CNN, image detection, YOLO 5, it can be used in healthcare. For example, you are having a use case for that. Preferably, you are trying to find out a social distancing in the factory, right? There are two workers. You wanted to find out whether the distance between them is less than that, and then you can detect, find a COVID tracker, right? Through YOLO 5. Same thing, you can use it for maybe in a retail shop or a mall. When people are buying, maybe you can use it in Reliance place, right? Your same algorithm works across industry. Image detection, how you detect a cat and dog is same as whether you detect in insurance industry, whether the car is kind of has a defect or not. Right? So, but reinforcement learning, the main problem is that one learning from one environment cannot be replicated. Why? Why do you think why can't we replicate one's learning to the others? Why do you think it is applicable? Why we cannot transfer the
environment, because environment will be different.
Yes, good answer. Environment will be different. With environments, each of this for each of the environment, our actions are different and our rewards will be different. A child, for example, your child.
Even if rewards,
Yeah,
even if rewards will be same, if you are training for mountain and you are training for plain road, that learning will be different to
for example, your child. The way your child learns is very different to that of any other child, right? Every child is different, right? That's why in reinforcement learning, we cannot transfer the learning that we do it from one domain to transfer it to other. And the last very important, design of reward functions. Design of reward function is very, very difficult. So you have to analyze the environment, you have to analyze thousands of actions before you can design the rewards. The third point is very, very vital. Designing a reward function is not easy. A PhD guy who has done a postdoctorate in maybe robotics for 20 years, he does the reward function. So most of the applications we use, reward function is already defined. We are actually is doing the application part of it. Clear? Any questions? Oh. So again, we will now formally define things. Okay. So there is an agent. Agent is interacting with the environment. Think of that. The child. Okay. Child is the agent. Environment is what? Environment is preferably he is, for example, riding on a straight road. Environment, that can be an environment. So agent is interacting with the environment through action. What is action? He's paddling the bicycle. States. So the agent starts maybe from point A to point B. So agent state is right now static. He is starting from the door of the house. He is taking one actions in the environment, means he is paddling bicycle in the road. What will happen? His state will change. Okay. So what will happen is that his state was ST, for example, it has moved into ST plus 1. Why? As the bicycle has moved from one place to other, it is maybe traveled a distance, and that state is getting changed. That state is temporal, means it is changing with time. For each state across time, we are giving him rewards. Okay, so how we can define a reward function? For example, you give him preferably three maybe poles. Okay, and so you do not, because the road is narrow and there is a wall in both the sides. So for example, this is the road. Okay, he is starting from S1, he is moving into S2. This is the environment. Okay, he is taking one action. So this is the wall and this is the wall. So you do not want him to thrash the wall. What you will do, you will have one obstacle here, you will one obstacle here, and you will have one obstacle here. And you will tell him that, or no, so for example, you put, so we are designing our reward function. Okay, so here we will put what? You will put something like a kind of a barrier, okay, so that he doesn't go there. Okay, you give for example, a bucket of toffee here, so that he moves straight. So this is a reward function we have defined. Okay, bucket of toffee, so that he goes straight, or okay. And how you can control the speed? You can give a speed breaker. See, I have defined my reward function so that the speed goes slow. So he's not able to control speed and go and thrash the gate. Right. So this is the reward function. So we are moving from S1 to S2 with action A1. So he might fall here. Okay. He might fall here. Why? Maybe my reward function is not correct. So I wanted to move this to here. Okay, then again he's doing, so S1, A1, he gets some reward, R1. Then again S2, A2, R2, different rewards. So it goes on until, what is the objective function? He goes from S1 to S2 without falling at least time. So this is the way we define our reward function. So that's a very, very clear that when he's falling at each step, we are measuring it and we are refining the rewards maybe. So it is moving into the next step with the different actions. And this is on the environment. So actually he's interacting with the environment. He is interacting with the environment. So what, so this diagram. So so what he is doing? The agent is interacting with the environment with action A. Okay. And he's moving into a state from ST t to st plus 1 is temporal, it is depending on time, and it is getting some rewards, and this happens until he is able to complete the object. So this is the basic of reinforcement learning. It is not easy. Okay, you have to define the environment. See how complex it is. Defining your environment. Each environment is different. I told you. You have to define that agent, define the actions, define the rewards. Is it easy? It's very difficult. Defining the environment, it takes ages. Everything will depend on that environment. Whether the road is straight, whether the road is curved, whether the road is slanted, whether it's a hill, whether we are going downhill, because when you're going downhill, the rewards and everything will be completely different. When he is going uphill, the rewards are completely different. When the road is zigzag, rewards are completely different. When it is raining, rewards are completely different. When it is hot, completely different. So the environment changes, your everything gets changed. So this is another part where you are playing a game. Okay, very, very important. So we knew that PUBG is banned, right? So for example, you are playing a PUBG. Agent is presented with S0 from the environment. So he takes some actions and he moves into the new S1, and where we're keywording R1. So this is same. So what it is doing is that you have a frame game. So you are proceeding with each of these episodes in a game, and maybe what is the actions you are taking, whether you are trying to kill that opponent or whether you wanted to hide. You can do two things. You are whether to going to hide it or wanted to kill others, or to shoot, wanted to shoot or hide. There can be actions. State means you are moving from one episode to other when you are moving through the game. And for each of the actions you take, whether you shoot or whether you duck, you get points to it. And what is your goal? Collect the maximum rewards. Okay, your goal is not to complete the game. Your goal is to get the maximum rewards. Why do you think your goal is not to complete the game? And when your goal would be to complete the game? A question to you. Your goal is to get a maximum reward when you are playing for the first time. First, maybe 1 month, because you don't know what is coming, right? But when you play the game around 1 year, you wanted to complete the game. So we are learning from our experience. Okay, that can be a second example of reinforcement learning. So rewards are very, very important. Specifies what is good in that intermediate state. So rewards, tell me what are the problems of a reward. So that's a question to you. Why do you think as defining the rewards is very, very difficult? A very basic thing that we have. So this basic thing needs to be taken care from our real life example. Why do you think is rewards are defining a rewards are very, very difficult? Can anybody answer? Why do you think defining rewards are tough? Hello, am I audible?
Yes.
Why do you think reward functions are what we should think of when you understand?
Yeah, first of all, if a reward function, uh, uh, if it is about training of walking, how should we convert it into the mathematical formula? I mean, so we can convey to the machine that this is the goal. That is the first, because environment nature will be different and we need to convert it to maths, right? So that is the first
Yeah, maybe you
problem.
have a data, you have a PhD scientist who have converted that reward. So he have understood the environment and you defined the mathematical functions for it. Okay. Very, very important thing that we will see is from our example. Rewards R1, R2. So do you think reward is a single reward we get? No, no, because from our childhood, when people used to entice us. So what your parents used to do, so we have three terms: first term, second term, and final term. Our parents used to tell, if you score in tomorrow's test, I will give you a chocolate. They do not used to say, at the end of the final year, if you give good result, I will buy you something, a video games. No, they will say the next test you score 80% out of the class test, I will give you a kind of a chocolate. Next term, so they tells that that class test was good. The next term, the coming term, you will get, for example, you score around 80%, I will give you a car, a toy car. Right? Rewards are based on time. It is not a single reward, but as we move our journey to be entirely 12 months, so we are preparing for 12 months for the exam. Divide it by 12 months. For each of the month, we are given a reward. Okay. And the final reward you give in L12, that is 12th month, will all be dependent on, now the question, whether it should be, the total reward should be averaged, or your current rewards or current actions is more important than previous actions. We will explain that, maybe that will come, that intuitive sense. I am trying to explain reinforcement learning in an intuitive sense. Why? Because if you get into mathematics, you are screwed up. You will not understand anything. Anything you will not understand. You will think that this course I am not able to understand. Why? Because from our childhood, our previous actions, that is in temporal. So what actions we did yesterday or day before yesterday is more important than your actions that you did previous 2 years. 5 years before, do you think our grades are more important right now? The 12th grade? No, because we are experienced. We have that, grades are actually not important for us. But when you got your first job, right, your grades were important 60%. Why? Because temporal, that time. So your previous actions, maybe couple of years before, is more important than your actions that are far away. Now you have to think that whether what type of weightage you should give, whether you should give what type of weightage you should give to your current actions, recent current actions, or all the actions, and what will be the time gap. So maybe 8, you are saying your actions are, for example, your result is, for example, getting a good marks. It is board. Maybe your last 3 months of preparation or rewards that you get is very important. That you decide. That's why people think that test results are pretty important. Other result, maybe when you are just got a promotion and moves them into 12, these are not that important. Or somebody will tell, I need to take an average out of it. So every month what you are scoring is very, very important. That depends. So that's why defining a reward function is very, very tough. Clear?
This if R1 is positive reward, then only it will go to R, means then this R2 will change, right? Means R2 is dependent on
Yeah.
R1, correct?
For example, R rewards, see, for each action, there are 3 actions I am performing: action 1, action 2, and action 3. Okay, on that environment, I am moving into, after I There are three states, S1, S2, S3 in environment, E environment. Environment is fixed. The exam is giving exam. You are doing a action A1, getting a reward R1, moving it into state 2, action 2, R2, then you are defining the transition. Then you say S3. It's complex. I will explain. That thing will come first. A3, R3. Now the rewards can be defined. Reward can be +1. Reward can be -1. Or reward can be 0. So you say that preferably you get more than 80%. That's when reward is +1. You get less than 80%. You get maybe you get less than 40%. The reward is -1. And between 40% to 80%, you do not get any reward. Now you have defined the reward function as this way. Okay. Now the total reward. So I am not considering individual reward. The total rewards can be R1 plus R2 plus R3 by 3 average. Or it can be R equal to alpha R1. Okay. So maybe alpha square R2, alpha cube R3. So alpha is maybe 0.1. So what I am doing, I am putting more importance to R1 than R3. This can be also reward function. Now it's complex. So it might happen that you define a threshold that if the reward is more than 80%, I will move up into the next step. Or else I will stay in this step only, S1. S1, you are taking action A1. Okay, what is the probability? So if the reward is for action A1, if the reward is less than 80%, you will not move up into S2. So if the reward is more than 80%, A1, more than 80%, you will move into S2. Then again you are doing it. So we will explain this. This is known as what? This is known as Markov's chain. For each of these things, you can have a probability and everything. So we'll see it later. Okay. So this is the intuitive explanation I wanted to give. So today's session is more on intuitively understanding reinforcement learning. From tomorrow, we will go into deep into these things. Okay. Just remember that reward function is not easy. Okay. So your current reward, your previous rewards, how you define it, whether you give more importance to current or past, everything is given. But only thing I want to highlight is reward is not a single function. It is divided into time. The total reward is a sum total of the episodes or tasks you do through the time. Why? Because from our physical, if I give you rewards at the end of the end of 1 year when you perform in the boards, I don't care. So you are failing. If you are failed in all the tests before in the 11th month, each of the tests in 1 month, you are never going to succeed in the board. You might argue, no, I will transform myself. No, it cannot happen. Maybe still 6 months you are failing. From 6 months you have transformed yourself still. But if you are performing in every test, it is very, very equal that you will perform good in boards, unless your paper get lost or something like that. These things can happen. So I will not think of a single reward, but I will divide the rewards into steps or time, and I will take an average out of it. We will see it later on. So that's the thing I wanted to highlight. Okay, so these are the consideration you should do in doing a reward. Okay. yeah, this thing what we are talking is that rewards is a cumulative thing and it is dependent on time. Very, very important, temporal. So you can take the cumulative rewards and you can add it without, so when you are using this equation, you are giving equal importance to your each time, equal importance. But when you are using this equation, what you are doing, you are putting more importance to recent time step than previous, because your alpha value will decrease this thing, right? So you are putting more stress on your current rewards rather than previous rewards. So it is up to you whether you wanted to discount it or you wanted to have a cumulative reward. So this is a decision you have to take. Clear? Okay, so so generally we use discounted rewards because from our experience. So whatever happened because of actions, your current actions depends your future rather than previous actions. Philosopher tells, right? What you do today defines tomorrow. So your current actions are more important than your previous actions. Clear? So we will always understand intuitively. If you go into the maths, you are screwed. You are not able to understand anything in reinforcement learning, neither machine learning. Reinforcement learning is very, very tough. Nobody understand reinforcement learning at 100%.
One thing, that if for example reward on R1, we got a reward R1 below threshold level, so that R1, that action will be performed again, and that time we will use the learning of that failing R1. Correct? Is my understanding correct?
I will refine your thing. Rewards are constant. So what I do is that when I will define a Markov's chain later on, it depends on the probability. Probability of a guy moving from state 1 to state 2. So threshold we will understand by probability. So we'll say probability of getting that reward that you define is greater than 80%. Then we'll move into the next step. So when a guy is cycling, I will say that based on my understanding today, he has 70% probability that he will move from step from your house to the gate without falling down, because I have seen him for the past 1 month, and based on that I am saying that he's a skilled rider. And the rewards that I'm giving, the chocolates, he's pretty confident, he's controlling the speed, he knows where to apply the brakes, his cycle is working fine. Then I will say that based on, I define the threshold frequency, threshold probability that defines whether I should move a guy from state 1 to state 2, giving a reward R2. Reward are same, but the threshold probability I will define whether he will stay on that state or whether he will move up into the next state through time. So your understanding was correct, but reward is fixed, but the probability will change. So we'll multiply the probability into reward to understand whether we wanted to move it into the next step or not. So this is, we'll understand that, for example, how a hidden Markov chain works. Okay, just hold on for this bit. Okay, so we have understood that why we are discounting it from our physical, from our real life experience. Can we take a break, because I think we have taken 10:30, so we can take around a 10 minutes of break, and we come back around maybe after 10 minutes. So I will start the. Is it okay if we take a break because we've covered much? Or we can take it later.
We can take a break.
Yeah. So I'm just starting the time so that So what you want? You wanted to take like how many? 10 minutes is fine, right?
Yeah.
So we'll start. We'll okay. We will start after 10 minutes. Okay. So, Should we start?
Yes.
I think we can start. So what were we discussing? We're discussing about the rewards, whether the recent rewards are pretty important, or all the rewards are important. So this we covered. So reward hypothesis. Let's see one example. So see, an agent is a rabbit, okay, and his goal is to eat maximum carrot before getting a shock. Okay, the rewards near the electric shock. The rewards near the electric shock, even it is bigger, more carrots will be more carrots will be discounted, right? And to discount the rewards, define a discount rate, and the larger is a gamma, smaller is the discounts, and smaller is the gamma, and the bigger is the discount. So what intuitively we are saying? We are saying is that for example, a rabbit is there. So this is a rabbit, okay, and we want this rabbit to eat the maximum carrot, okay. So so now when you are defining the reward functions, if I put equal reward in each of the block, okay, then what will happen? And if I put more rewards in places that are dangerous, what will happen? Why we were putting these type of things? Why not put the equal rewards in each of these things? So this also one carrot and this also one carrot. Instead of putting 3 carrots here and 3 carrots here, why do you think we use these type of reward functions? And this is very, very important. So what happens is if we put equal reward, so see the rabbit has to then what traverse the end. You have to go there, you have to go here, you have to go to the left. This can be one path, or he might have to go to left and he might go up, or he might go here and here. So there
I
is
bring it
several
screen.
ways. Yeah. Oh,
Yeah,
sorry. Okay. Sorry. Okay. I will again explain. So what is my screen visible? So agent is a rabbit. Okay. His goal is to get the maximum carrot before getting the shock. So it is your goal. It is your objective function. Closer the agent goes to the shock, it gets more dangerous. Okay. The rewards near the electric shock is greater, okay, and will be discounted. So, so the larger is a gamma, smaller is the discount. So the agent cares more about the long-term rewards. If smaller is a gamma, then bigger is the discount. Agent more cares about the short term or the nearest. So what I am saying is I have a rabbit. Okay. The goal is to eat maximum carrots. So how many carrots are there? 1, 2, 3, 4, 5. And here is 3, 3, 6. So 11 carrots you have to eat, right? That's the objective. Now the rabbit can go through this path, this path, this path, right? So get the maximum carrot, or he can go to this left and right, or he can go to straight and this one, or he can go there, and there are a lot of ways to do it. So what I'm saying is that if I put one carrot everywhere, do you think it's a right strategy, or I should put more carrots regarding near the electric shock, right? Now tell me that we saw that our total rewards are what? R1, R2, R3, R4, R5, and here is this I take as a R6, and this as a R7. This is R7. This is R7 and R6. Tell me that, and the rewards are different. So R6 has a greater reward. It has a higher reward than R6, and R7 has a higher reward. Now tell me that first question, whether all this thing will have equal rewards, or I will put more rewards in places where it's a electric shock. That's the first dilemma. Second dilemma is whether I should put more. So this is simple, right? So I will put a gamma to it, right? So I saw that. So next question is that whether it should be uniform, or the reward function might be this one, R1 plus alpha R2 plus alpha square R3, and goes on till alpha 6 R7. So first tell me whether we should put like equal carrots across, or should I put more carrots to places where there is danger, electric shock, when I am designing. So somebody tells you to design the environment. So I should put more here, right? Why? Because the rabbit will eat this, go there. And why it will go there? Because I have to move the rabbit from here to here, right? Because there is electric shock. So there is a concept we'll explain later on, is exploitation or exploration. Very, very important. We will explain this, exploitation or exploration, what it means. Whether the rabbit should exploit means it should not move here. So it should eat the rabbit, eat the carrots in the nearby grids, and it should be happy. And it should try to maximize them. Or it might wanted to explore into new areas. So in order to explore more areas, you should provide more incentives so that rabbit can move to places where it's danger and it gets the electric shock. When it gets the electric shock, then it remembers that this is a place where it gets electric shock. Therefore, I have to put more rewards here so that I can get that action. So I can experience that whether I have that actions and what is the consequence of that. So with more rewards, there are more risks also. So that's the first consideration. That's why I put more carrots to places where there is electric shock. Okay. Second consideration is whether the reward function would be vanilla type, just a cumulative sum, or I will put a gamma. So larger is the gamma, then what will happen is smaller is the discount factor. That means it cares about more on long-term rewards or short-term rewards. Should I make a gamma to be smaller or gamma to be greater? Intuitive senses will move the gamma to be smaller. Why? I have to care about a short-term carrot or nearest carrot so that it remembers. So when it gets a shock, so remember it has ate 3 carrots. So your previous actions are more important than old actions. Therefore, I keep the gamma to be very, very small. So in real life, these are the situations you have to face. So you don't have to design it, because designing this is very easy. This is simple. In complex environment, there can be several constraints, and in order to develop that constraint, it's very, very tough. Okay, but only point I wanted to highlight is that these type of dilemma you will face. Okay, and the reward, defining the rewards is one of the most important and toughest part of enforcement. Okay, now I will touch upon this, is what is policy, what is value function, and what is the model of the environment. These are the components of the agents. So these are definite terms. So if you do not understand this, you will not able to understand what is coming in the next classes. So the first thing is that policy. So what is the policy? Can anybody tell what is policy? It's very, very simple. It defines the agent's way of behaving in a particular environment. So mapping the perceived states of the environment to actions to be taken on those states means nothing. So you have a 4 grids. 1, 2, 3, 4. You are present in this grid. This is your starting point, and you wanted to move up to this grid. This is your ending point. Okay. Now, you will do is you will S1, you will take action A1 and you will get a reward R1. So S1 is what? S1 is the state 1 in this grid. Okay, so this is the S1. Okay, so this is the so the state 1 can have values. So rightly I can think of state 1 to be 0. So I have randomly initialized. I will put everything in 0 right now. So action A1, what is the action? Action is up. So you are taking up because I can only take up from here, right? Left is not there. Right is not there. Down is not there. So from each of so just explain it in a better way. Okay, so how many states are there? S1, S2, S3, and S4. So states are S1, S2, S3, and S4 states. What is the action? Tell me. Actions can be up, left, I will define it in a better way. So it can be left, right, up, and down. And maybe you have a reward function.
Cross.
Up, down, left, right, up, down. A cross I am not taking. Cross, okay. Because left, if you move up and down, it should be cross only. This is cross. Up, you move up and take a right, it should be cross only. So I'm not defining because it is a redundant action. Okay, and the rewards are maybe I am defining it to be -1. -1. Okay, and +1. And okay, so these are the and what is the environment? Environment is a grid world. So the environment is grid world. This is 4 grid, so we call it to be a grid world. Okay. Now mapping. So what I am doing? So here I am from S1. I am doing an action A1, right? And I am getting a reward R1. So what is that? S1, I am doing an action 1. So I am doing action 1 means I am doing a left. Okay. And left, right, or like anything, right? So I can define it as this one. So when I do an action, so you can just define it like this way also. So S1, if I do an action left, I stays in S1, right? Or I do an action left and or I do an action right, or I do action down. All the cases I am in the state 1 only. I can move up into state 2. How? If I do an action up. Okay. And for each of these, I'm getting a reward. So I'm getting a negative rewards. Okay. Why I'm getting a negative reward? Because I am not moving. Right. I'm not seeing now I'm moving from S1 to S2. I'm giving +1 because you moved up S2. Then again, S2 is, for example, you are doing what action? S2. You are moving left. No, you are moving left means on S2 only. You are doing, for example, now up. No result. It is on S2. When you are doing, and these rewards associated with it is what? The reward is -1 because you are staying on that. Now I move this thing to S1 if I go down. Okay. So when I go down, I move up into S1 with reward what? Reward is -1 because I am again moving into the same state. Okay. Or else you can also do is that if it stays in the same state, you can define 0 also. So I am saying it if it is stays in the same state, you can define 0 instead of -1. This is 0. If I move up into a state that is below, I will give -1 because I am again come back to the origin. Okay. And if I move up into the next step, it is +1. So it can be -1, +1 and 0. Then again from S2 to S3, you can define, you know that, right? From S3 also, what I have to do if I move up into S3, I will have to do what? I will have to do a left. So left is the only action I can do to get a reward +1 to move up into S3. And then again S3 may you do left, you again move up into S1 and with reward -1. And for any other actions like up and right, up and right, you get reward to be 0. Okay. And from S3 to S4, you have to make down. Then you move up into S4. And S4 is my final state. So when I went to S4, I wanted to give more rewards also. So if I like, I can have a 4 also. So when I move from S3 to S4, I move up into 4. So that with the greed of more rewards, it move from here because I am near. So I move into 4, I go into S4, and then S4 is a terminal state. So this is a Markov chain. We'll see it in Markov chain in detail. So just I want to explain what is the policy. Policy is a mapping of the perceived state to the environment to the action. So these are the policies. So what are the policies? So policies are nothing but initially all the values are 0 here. So policy is based on this. You have 4 actions. And 4 actions left, right, up and down on state 1. With those actions, so these are the policies for state 1. And I take a policy to move up. So mapping of the perceived state to environment to the actions to be taken on those state. So this state 1 can have 4 policies, right? That is R1, R2, sorry. So you define policies like, you can define this to be S1. From S1 you wanted to move to maybe S2, right? So S1, if you define it to be A, from A, so the policies are what? You can define like this way, policy table. Okay. So states are S, actions are states, these are the state ST. Here is ST plus 1, 2 state, right? For that you have actions Okay. So you can have actions. So you can have actions. Here is the transition probability of that actions, and you have the rewards. What I am doing, action S. So there are 4 states, maybe like this grid world. 4 states are A, B, C, and D. So then A, I'm going to from A to B, for example. Action is up. Transition probability you can define to be 0.8, for example. If it is 0.8 only, I can move, else I will move into the same state. Reward is maybe +1. So this is actually a policy. Then again from A, so this can be 1. So from A to, now from B to C. So you can define from B to C. Again, we will give them some action that is left, that is right. Transition probability is, what is a probability? So transition probability can define to be anything 0.7. So I will say if it is 0.7, it will move, else it will stay in the same state. 0.7, and I gave a reward of +1. From C to D, reward is what? This down. So it's down. Transition probability is maybe 0.5, and the reward is great. I give it 3. And then for other from other transitions, it also define from A to A, you will define -1 and all. So this is a policy. Actually, this one row is a policy. So policy is A, B. This can be a policy. From A to B, this can be a policy. Policy will contain what? It will contain state, it will contain actions, it will contain some transition probability, or it can have a reward functions. Okay. We will explain it in just, it's an introduction. So what is a value function? Value function means initial value is what is there. It is 0, 0, 0, 0. All the initial values are 0. Now with one move and all, with different moves, I wanted to iteratively improve the values. Okay, our goal is to start from 0, 0. Maybe a next iterations, it becomes 0.1, 0.2, 0.3, and 0.4, right? Means with how it is moving means maybe it moves here, here, here. Okay. It is episode 1. It is episode 2 if you think. In this way, each of the episodes, my value is getting changed because I am taking different action with different probabilities based on this policy table. And it can go infinite time. So we'll explain that how to control that. Maybe at certain episodes up to E100 or E10, I will say I will stop and I will take the value. So it will start with the value function, and it will iteratively and change the values accordingly. And I will stop where I am not getting any incremental benefits. Okay. And I will have the model of the environment, allows conclusion to be made how the environment will act, might predict the result of the next state and the next reward. So model of the environment. So what is the model? This is the model, the entire thing. Each row is a policy. P1, P2, P3. Your model is the entire environment, this square. And the value function is the value you get. So the final table will look like this one. So the final table will, so final table you are not able, so final table will be like, you can describe this as this one. 3 rows. Okay. This is policy 1, policy 2, policy 3. This is what? State T. Here state T plus 1. Here you have what? Transition probability. You have rewards and you have value. You have so you have value. Okay, and yes, you have this grid world again. You have A, B, C, and D. Okay, and you are making a transition from A first move. So it's a first episode. You can think of this as an episode. A1, you are going AA. From A, you are going to B with some transition probability 0.6. Reward is +1. And value is something you start with 0. So the values would be first 0 for each initial values. So you will have some value 0.4. It has changed. Next policy is maybe A. From A to A. Transition probability is very 0.2, 0.5, -1 reward. Okay. And the value is maybe 0.1. Okay. Okay, you will have an action also here. So action is preferably you are moving up. Here you are moving left. Then again A to A, 0.2. Reward is -1. Value is 0.12 to the right. All are reverse 1. Then policy 4. A to what is a policy? A again. Transition probability 0.1. Rewards are -1. Value is 0.3 and it is left, right, left, down. So I will take this up. Why? Because my value is greater. So I move up. So these are the different policies. These are the transition probabilities. These are the rewards. These are the values. And these are the actions. Now I take these actions as a whole because its value is 0.4, highest value. That's why I'm saying this value is 0.1, this value is 0.2, this value is 0.3, and this value is 0.4. As it is highest, I move on. So this is C. So much of complications just to move from here to here. So this is episode. So episodes just for A. You have to do it for B as well as C. This is episode E1. So after the episode E1 is done, so what is happening is that you have E0, where we have all the values. Initial values are 0, 0, 0, 0. Then E1 is there, first episode. My values gets changed to 0.2, 0.3, 0.4, 0.5. These are the maximum values. We saw it, how we are calculating it, right? So we'll go into deeper in the next lecture that actually will show you. Just understand the concept. E1, E2, then E3. Again, it will iterate and its value is going to be changed. So after maybe 10 iterations, I am saying E9 value is maybe 1139 and E10 values are very, very close. So it is 0.9, 0.9, 2.99 and 8.99. So there is no point in continuing more. So it's close at episode 10 from E1 to E10. And these are our final values. And the robot ends here. It starts with this one and here it ends. Now it has learned everything at which step. So now you put the robot here, it will learn. it will go here, 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 based on these iterations. Is it clear? So this is the thing I'm trying to explain for. This is a definition, but you have intuitively understood that what is there. So these will be covered in different classes. So what is policy? What is the value function? And what is the model? Model of the environment are nothing but episodes. Episodes we talked about. Value function is start with 0 and each of the episodes is value function gets changed, and policies are from A1, A, what action I take. So for policy, what we see, state 1, S1, we take action 1 and get a reward R1. So this is nothing but a one policy. And the value that it, after getting, doing from state 1, it takes action 1, gets a reward 1, and its value function gets changed. So value means after getting the reward, what is the value of this state? Okay. Why we calculate the value? Why we are intuitively calculating the value? Why do you think we are trying to get that? Because we saw that, right? That we are taking the maximum value. So without value, how do you know that I should move into S1 or S2? Whether it is better to remain in S2 or whether I move up into S1 to S2. So if the value is more, I move up into S2. If the value are same, I stay in that state only. Your robot is not able to learn all the values. So I am saying S1 to next state, S2, S1 to S1. There are two states. This value is 0.2, its value is 0.2. Robot is not able to decide. Maybe he randomly chooses. In this type of scenario, when the value is same, it randomly chooses and then it corrects itself. So somebody was asking, right? Random value, zero value, it doesn't matter. I start with a random value, zero value. With iterations, I will get close to it. It doesn't matter whether the initial values are what. Only matter is a final state value, and it will learn the values. So random value, zero value, it doesn't matter. Maybe you take a bad value, what will happen? The robot will take time to learn. Maybe it takes around 2000 steps to learn. And if you give a correct value from your experience, it will take 50 steps to learn. So you are saving on the resources. That's it. If you give a bad value, it will take more steps to get into the right value, right? So it takes more steps to learn. If you get bad values, it gets more steps to learn. If you get good values, it takes less steps to learn. So it's learning at a resource constraint environment. Agreed? Any questions? So at least this will again cover in next class, but at least you are able to understand. Why value function? Value function is because we need to know whether the policy that we are taking is correct or not. Whether it's better to keep into a current policy or whether I wanted to move up into new policy. And policies are nothing but a set of rules. If you have a state 1, if you take action 1, if you take a reward R1, this is a policy. And each of the policy will have a value. Because why? I have to compare the policies. If somebody tells me policy 1 is better or policy 2 is better or policy 3 is better, I have a value function 0.1, 0.2, 0.3. I take 0.3 because it has a highest value. Now you can define your own algorithms to calculate the value. And model of the environment. So entire that policy has value together, the table is the model. Any questions? This is very important. What is policy? What is value? What is model? Now you tell me what is the problem here? Is it easy? What is the problem? In complex environment, what will happen? Can anybody answer?
We can have same value if there are so many states we have. We can have so many same value. So
Good.
it will be.
Yeah,
So
that
most of the time it will be a random only. It will go if same value.
why you are saying that? Because see, I can start with any value, right? And with the help of that, if I know the policies, I will correct the value.
It will taking time to learn, right? If
It
same
will
values
take
are
the
there.
time to learn, but one thing we have not at all considered is we are taking some discrete environment, right? It's very simple function. I am here, from here I have to go here. So it is discrete. Okay. And there are some rules I can associate, right? It might happen if the environment is complex, right? I have no rules. I have no rules means I cannot design the reward function. Simple. No rules means no. Reinforcement learning doesn't require rules. For example, the environment is so complex that I cannot use a rule-based reward. So we will talk about that later. That is known as model-free environment. I cannot design the rules because it's so complex. Learning a robots, there can be 1 lakh of rules. Is it possible? Then I will take around 10 years to train the robot with different simulations. So much of money. Do people don't have so much of money? All right. Then that we will cover in later stage is, for example, what we will do. Okay. So at least we have understood. So this we'll cover later on in the classes. Just an introduction of what is policy, value, and model. Okay. Now, what is that? Next is that, again, I told you we have covered it. What is a agent and what is an environment? So upon receiving QT and RT from the environment, the agent takes action A1, the environment receives action A1 and emits the observation and provides a scalar reward RT plus 2. Nothing, same thing. So we have a action A1, we have a state QT. So this is a state. This is a state QT. We move from QT to QT plus 1 and we take an action AT to move from here to here. Uh, uh, and what it does is that it provides a scalar reward RT1 to me. So with this action A1 on state S1, I move up into S2 with a reward RT plus 1 and that reward is given. That's it. That's an agent and an environment. So this is where an agent is interacting with the environment. Any reinforcement learning, there will be state S1, there will be action A1, there will be reward R1. Then I move up into S2. So I move up or not, that depends, right? That depends on the transition probability. And that is solved through Markov's value chain. We'll understand. Right now, you think that S2, A2, R2. Okay. And I get a reward of R2. And I pass the reward to this. Now it rewards is positive or negative or neutral. That depends whether I should move up into this state or not. Okay. Now, again, the history and the state. So we have to store this, the entire table. So storing a table is very easy for normal tasks. So you have OT, first state, you have a reward A1, R1 and give it to A1. From there you move up into O2, R2, A2. So this entire thing needs to be stored in somewhere. And you will require, so this is a kind of a scalar, or these states needs to be stored. Okay, and based on that history, actually we are taking our actions. Okay, so these are the business rules. Still I cannot call it to be a full reinforcement learning, because still there are some rules I am taking, and that rules are stored in some table and I am taking the actions. So this is true when you have a small, yeah, you have like, for example, not complicated environment. In complicated environment, you cannot do because it will go to 1 million. Okay. Now the history and state is over. Now, again, the same thing we talked about. One is environment state, one is agent state, and one is information state. So the environment state, ST is environment's internal representation. So same as that. So we talked this, right? So we talked about ST and ST plus 1. These are environment state. Agent state is, I can now, I can take about a particular, if there are multiple agents. So here we are talking about a single agent, we can call it to be ST plus 1. If there are multiple agents, so what will you do? You give a A. So ST plus A is a state of action for agent A. ST plus B is the state of agent B. So with environment state, in environment there can be different agents, simple. In environment, there can be different agent A, B, C, D, E, F. So from environment state, we'll have state of each of this agent. And information state, the table we saw it. So for agent agent A in environment agent A, this entire table that we store are information state. So information state can be, I have this state ST, I move up into ST plus 1, I have an action, I have a transition probability, I will have values. This is the information state for agent A in environment. And these can be different. So this is not a single table with each of the episodes. So I divide the entire, for example, I have around the entire episode into 12 hours, for example. For 1 hour, 2 hour, 3 hour, 4 hours. So each would be an episode. E1, E2, E3. So each of the episodes, I will have this agent state, information state. So each of this you can talk about environment. So I am talking about total environment here. So I'm breaking it into times. So this is an environment state for that one, means time. So this is an episode. This environment state, we can call it to be episodes. So environment one, not environment, sorry. So this is an environment. There will be an episode, and for the episode, there will be an environment state and there will be agent state. Okay, so E1 is an environment step. Okay, why? Because the total environment is E. So each of this step, there are 12 environment steps for the total environment. For each of the environment state, there will be an agent state and there will be information state. So if I draw it, this should be environment. Here, environment state, E1, E2, E3. Environment state can have different agent state. Agent A1, A2, A3. Agent can be divided into information I1, I2, and I3. See, from environment, I go up into environment state, from agent state to information state. So information state is a table that we're talking. So see the complexities of this part. Okay. Now, fully observable environment and partially observable environment. So what I am saying is that if the simple environment, all agents directly observe the environment. So tell me that you are using a robot. Is it right now it can be fully observable because you have the cameras, you have the sophisticated deep learning technology to capture everything. So full observational environment can be possible with technology. But in certain cases, and you know the end goal. So you know that the robot has to travel from point A to point B. So it is fully observable. You know the end goal, you know the starting goal, you divide it into episodes. If you and you know the environment, you have agent A1 moving from state 1 to state 2 with some action 1, you are getting a reward 1. This is fully observable. But in certain cases, there is partially observable or no observable. So for example, you are trying to predict the stock market. You do not know what will happen tomorrow, right? So this environment is not known. What type of reward function you will design is complex, right? Based on the historical data, you cannot define it because a stock market is kind of what you call it. It is more on stochastic, right? It's not deterministic, it's stochastic. Means I cannot rely on that. Okay, so all the relevant portion of the environment are not observable. Right? You wanted to train a car, right? You train a car in Bangalore. You move that you train a car in San Francisco, or you train a car in New York, and wanted to bring the car to India, where people do not cross in zebra crossing, right? Do you think it will able to do it? It's partially observable. It's not fully observable. There can be several instances that I have not observed, right? A guy can jump inside my car because he's doing a suicide. How will I able to know whether this guy I have accidentally come inside a car or this guy is trying to do suicide? Some speed breaker was not there. I am training the car for 1 year. BMC has come and put a speed breaker. My entire learning has gone in a toss. Some because of that COVID thing, some roads are blocked. I trained the model on that. That road is not taken, or some metro construction is going on. Do you think that is a fully observable? So in complex environment like training a car, training a robot, is partially observable, but fully observable is playing a Pokemon game, or playing like a chess game, or training a bot to for example, to reinforcement learning on preferably a text this is fully observable. But partially observable is areas which is complex and the environment keeps changing. Any questions? Should I move ahead, or do you have any questions? Hello. Should I move ahead, or you have any questions?
You can continue.
Okay. So agents taxonomy. So goal to optimize the value. So what is the goal we are taking? So we are trying to model the environment. So we do not know the environment. With reinforcement learning, there is an environment. With I divide the environment into episodes, E1, E2, E3. Right? With episodes, I have I am moving from state 1 to state 2 with action A1 with reward R1 for agent A. Right. So this is the modeling. I'm modeling the environment. So I do not know. If I know the environment, I can use a business rules. I do not know environment, so I'm doing a proximate. So I'm trying to like guess the environment. So it is E prime, and that is happening through here. Dividing the environment into episodes, and then I'm taking from state 1, I'm moving into state 2 with action A1 with reward R1. Policy based. Okay, goal is to optimize the policy. Okay. So I will explain this. What is the difference between a policy-based and a value-based approach? So that I will explain. Just park that until now. So just learn that policy is I can optimize the policy. Policy means I can optimize the. So policy is what? Policy is set of values. Okay, so we know that policy is, it has state st. I am moving into st plus 1 with action with some actions. We have transition probability and we have rewards. So this is the policy. So policy is nothing but a state of values. So what I can do is that I can do a value based, means I will try to optimize the value. So for example, policy P1 has value 0.2, P2 is as a value 0.8, P3 is a value of 0.5. So what is the policy here? Policy is I am moving from state S1 to S2. Okay, so policy is I am moving from S1 to S2. So now how will you say that which policy is greater? So you say 0.5 is a good policy. What is 0.5 policy? 0.5 policy is go up. So each policy will have action, right? So I am saying I have to move up. So this is one policy. And that policy of moving up is a policy, and that policy is decided by values, value based. So which has the highest value, I take that policy. So what I do, I can do a value based, so goal based optimization. I can optimize the value and get the highest value and select the policy which has the highest value. Policy based is I can directly optimize the policy without knowing the without going into a value based approach. So for example, I can directly say that this policy up is a better policy because how I am trying to do it, because I directly compare the policies instead of comparing the values and then deriving the policies. So instead of value, so these are same actually. So in value based, what I have, I find out the optimized value, okay, and find out the policy associated with those values. In policy based, I directly optimize the policy. So here we have value. From value, we are deriving the policy. So we have value like 0.2, 0.8 and 0.9. We take the value of V3 as 0.9 and see what is the policy associated with V3. Here we do not take that lengthy step. We know policy P1 has value 0.2, policy P2 has value 0.4, and policy has P3 has value 0.7. I take policy P3 directly because I know the underlying functions. I don't have to use the value to get it. Maybe I know this policy has some normal distribution preferably. So I can directly find out the policy instead of going into the value. Okay, so I can optimize the policy. Same thing. I can optimize the value and then derive the policy. And the third is that model based. Model based is what I do not care about the value and policy. That means I am not relying on my past experience. Past experience is not important. I will let the model figure it out for me. What will be the optimal policy? What will be my reward function? What will be my state? Everything. So in complex tasks, we use model based. So for example, Monte Carlo simulation is a model based. You don't have to do anything. You just pass a sample. So it's model based means I take 3 samples. So I will say these 3 samples will define my environment because I don't know the environment. And if I do a value based and policy based, I told you, right, training a robot, it will take me ages. I train the robot 10 days, pass the data to a model based will define all the simulations for me and will train the robot. It is cost effective. because I don't have time to see the entire environment. Value based and policy based means you have to you have to see all the business rules. Model based is nothing but a sampling. I train the robot 10 days or 2 days, take the value and use a model to do that. And then model will like use different simulations to guess that function. So here what I am doing is, for value based and policy based, I am using business rules to guess the function. Here in model based, I am using a sampling to and let the model figure it out. It can be deep learning. It can be, this can be deep learning. This can be for DQ and deep Q learning network. It can be for example, Monte Carlo. Okay. There are different algorithms we learn. TD, temporal difference, SARSA. Okay, so all are model based. Okay, and policy based and value based are nothing but business rules. Very important. Do you get that? This is for sophisticated, and this is for generally for simple environment. But this is more accurate. Why? Because I have business rules, so I have every and each possible cases. Model based takes approximation, right? So this is a real functions of the environment. Here we take an approximation based on the sampling data. Is it clear? Or you have any questions here? What is the difference you have understood, right, between the model based and value and policy based? Any question? So for training a robot, training a self-driven car, we'll use a model based. And for playing a game like chess or a Pokemon, you will use a value based and a policy based. Any question?
No.
Okay. So value based is the value is predicted for the future rewards. Okay. So it is the value based is nothing but I told you, right? So this is the value of the function, and these are the rewards. Okay. So we talked about, and this is an expectation. So this is the transition probability. I'm talking. This is a transition probability, and these are the rewards. So we multiply the transition probability with the reward to get the function. Okay. So we will see it. For example, we will discuss it in. This is just an introduction. So what I am saying is, so again this concept. So you have these 4 states. You have 0, S1, S2, S3, S4. So this is the terminal state. It have what? It have 4 areas. So we will say states are S1, S2, S3 and S4. The rewards actions, or you can talk about actions, are left, right, up and down. Okay. Rewards are 0, -1 and 3. And we'll have a transition probability. So I will write S1 S2. How beautifully I am going to S3 and S4. See how beautifully I will design the through hidden Markov's model. S1, which are the things you will do in S1? So if I have a action of left,
Left down.
down, you say, and right. Okay. So
Right we can go, right? S4.
no, this is blocked. Left you cannot go. Right you cannot. You are in S1. S1.
Okay. As per
Light.
policy, we should go to S2 only. Okay.
Yeah, you cannot go. Okay, because there is a wall. There is a huge
Okay. Okay. This is
wall
all.
to it.
Okay. Okay.
Okay,
Okay.
you
Okay.
cannot go it. Okay, so this is the part, and each of them has a transition probability. So transition probability 0.2 is very important to define a transition probability. Else what will happen is that it will be a kind of a random. So I'm paying zero point 0.2 has a, because anything can happen, right? You cannot say. It's a stochastic process. It's not a deterministic process. So everything will have a transition probability. Right now from S2, tell me how we can go from S1 to S2. So
Up
0.2. So what will be the probability of this one?
0.8.
Good. 0.8 will be the probability of this one. And what is the action? Up.
Up.
S2, again a transition probability of 0.3. What is the transition probability here? Left, okay, and right.
Da left down now.
Left, right. Now I take a
Left.
down.
Okay.
What I did, move S1, so down, and I take a probability of preferably 0.1. Okay. Okay, and I'm not defining. So here the rewards, if you think reward is what, in same state I
0.
am making a reward. Same state I am making a reward 0. Moving into the next, I am making a reward +1.
+1.
Is moving into the again a previous state, I am moving up a reward of -1. Okay. Now tell me from S2. So it's a 0.3, a transition, and 0.1. From S2 it moves up into S3. Okay. So what is a transition probability? 0.3 plus 0.1, 0.4. So 0.6 is a,
0.6.
okay. And from S2 to S3, how can I move to S2 to S3? It is right. Now S3. So what will happen? What is the probability of staying in the same S3? So I
0.4.
take it 0.2. Okay. What is the
Point.
so I can move up, or I can move right. If I move up also S3, right also S3. If I move to the left, that means I move into S2. So left and transition probability, think of 0.2. Okay. Now from S3 to S4, very important. I move down. Transition probability is 0.8. Not 0.8, 0.2, 0.6. 0.2 plus 0.2, 0.4. 1 minus 0.4 is 0.6. What is the okay, and the reward is 0 and reward is -1. Here the reward is 3. And S4 is, I don't have anything. S4 I have reached, I do not have any. I don't want to do up, down, anything. I want to close it. So this is the exactly an hidden Markov chain I have drawn. So what is the reward here? So I have to calculate the individual reward of S1, S2, S3 and S4. So what is the reward of S1? So I can do it like this way, right? 0.2 for state 1. I will find it for state 1. So I will have to have a state 1 plus state 2 plus state 3 plus state 4. This will be the cumulative reward. This is only one go. So you have to do a different, now my value function will change. Okay, so that we will define. So what will be the rewards here? So it can be 0.2 into the actions. Now you can define the left right into 1 or something, but I can define it to be left. So it is 0.2 into left plus down plus right plus it is 0.8 into up plus then again it will start, right? So 0.3 into left and right for S2 and okay, no, I have to multiply this with the reward also. Sorry, this is
So, but we can left plus down plus R, we can take reward itself, right? 0, 0,
yeah,
0 means
yeah.
0.2
So
into
you
0,
can
0.
so you can do it is that I'm clearing. I am just writing. Sorry, this is wrong. So what I do is that I do is S1. So S1 is what? 0.2 into the reward of each of them. So left is -1 plus down is -1 and reward right is -1.
0, right? Not -1. Because there is no other way it will go.
Okay, sorry. Right. It is 0. Sorry. It should be my mistake. It should be 0 plus 0 plus 0 plus 0.8 into what? Into up
1.
1.
Up
So it
1.
will be 1. Okay. Plus 0.3 into left and right is 0. It is for S2. Okay. 0 plus
Plus
what is the priority?
into 1.
I'm saying 0.2, right?
Point,
0.2
no,
is
point 1.
point 1. 0.1 into
1 into
-1
-1.
plus
Plus 0.4 into
0.6. 0.6, right? 0.6 I move
0.6, 0.6,
0.6 into
0.6
plus
into
1.
plus 1.
For S3, what is that? For S3, S3 is
S3
0.2 0 plus 0 because left and up and right is 0,
yeah.
right? Plus plus it is what? It is 0.2
0.2
to -1 because it is moving here. 0.2 is -1 plus 0.6 into 3 because I'm moving up here. So see the total rewards you can know. So now I have not added the discounted factor. So you can add a discounted factor of lambda equal to 0.01 and say that whether your immediate rewards are more important or not. This is, I am giving equal importance to each of the rewards. So you need to put more importance, so you can just multiply with lambda and do it. Okay, so it is instead of S1 plus S2 plus S3 is for S4, it is S1 plus lambda S2 plus lambda square S3 plus lambda 4 S4. Oh, no. I will not define it like this way. So you can define it to be S1 will have less importance maybe. Lambda cube plus S1 plus lambda square plus S2 plus lambda plus S1, S3 plus S4. So what is happening? It is revert. Okay, so associated with the revert, right? So even lambda 3 means lambda cube 3. So you have to multiply this with lambda cube, lambda cube. Why I'm saying that? Lambda cube 3 means S1 gets less importance, then S2 gets importance, S3 is very, very important. So from S3 to S4, this revert is very, very important. So I can add a discount factor as well. Is it clear? So right now I'm saying S3 has more importance than S1 and S2. Because 0.01, if you square it, it becomes more or less. All right. So this is the thing. So if everybody has understood, then we will cover it in details in hidden markers. But still, you will get right how we are calculating the revert and why we are discounting it. Is it clear, right? So total reward can be sum total of this one, and then we can also discount it if you wanted to give importance to this one more than this one. Okay. So okay, so this is the reward function we are talking about. So don't think about these formulas. These formulas will kill you off. If you intuitively understand, we have understood. So what is this expectation? Expectation are nothing but the transition probabilities. Now tell me, in complex situations, this transition probability is very difficult to calculate.
Correct. If we have so many ways to go, so many states, then transition
Yeah,
probability will distribute like anything.
anything. So that's why we always using model free. Model free means this expected value that we take a sample, we just train it in 3 or 4 observations, and we let the model to figure it out. So it will do by sampling. That's why your Monte Carlo is very, very important. I will explain. So we will first, next class we will understand what is value based, what is policy based, what is the limitation of value and policy based. We still know it, right? That if the number of states are more, then value based or policy based will not able to do it, because the table will be so much that you cannot store it in your any memory. Think intuitively. We cannot store it in any memory, because for example, if you're a robot, we'll have 1 million row for this transition table. All right, several state, here to here, here to here, here to here, here to here. You will not able to do it. That's why this expected probability I'm not able to calculate in complex environment. What I do, I take a sample and then let the model figure it out. That is the Monte Carlo simulations we're talking about. That is model free. We are moving from model based to model. We are moving from what? We are moving from value based to a model based, not model free, model based.
Okay, so you mean to say for we will use model for probability to predict which way it can
Yeah.
go, and on top of that we will have this whatever value based or business
No,
model.
I am not value based. I am moving away. So what I do is that I will do is, see, the expected everything, this expected probability, these rewards, everything I will try to train. So what I do is that, for example, I have a distribution. So take 3 samples. So 3 samples has expected value is, for example, 0.1, reward is maybe 1, and you have the states and every actions for 3 observations. This table is for 3. It's just like Bayesian. You have 3 observations. So how you do it? If there is 3 observation, a data scientist, you are a data scientist, you have 3 observation, and your client says, I want a model out of these 3 observation. I will tell you, no machine learning model is able to predict. If you have 10 observation, your client says, I want a linear regression model. Will you be able to do it? Your model will be overfitted model. How will you do it? you do a Bayesian regression. So I don't depend on data, I depends on the distribution. So I say I will continue to do the testing. So when I take a repeated samples, then what I say is that I will able to mimic the distributions. All right. So with 3 observations, I can actually predict it through Bayesian methods, right? So Bayesian, what did Bayesian does? Bayesian does is that you have some prior belief. So you will say this distribution is a normal distribution, right? And you create on creating the samples. So as you create more and more samples, your belief will change. So you will think the distribution is Bayesian and you do the sampling. So after 200 samples, you will know that no, the distribution is not Bayesian, it is Gaussian. Okay. And then still you have a very bad result through Bayesian. Or else you get some, like you get you get a better result than normal frequency based, right? With Bayesian, with Bayesian thing, because what you are doing is that you are just thinking that what is a distribution, because when you think of a distribution, so see, there is a concept. So in probability, there are 2 ways to, people don't know, there is 2 ways to find a probability. Okay. This is a very, very important concept. Just listen. Probability, there are 2 ways from the data. That is a frequency based. You know about normal distribution. We think about central limit theorem. Everything is frequency based. So you have a data and you are able to do that. But there is a Bayesian statistics. Bayesian statistics thinks that I will not require data, or the data here is very, very less. So I will, from my prior experience, I think the purchase pattern is a beta distribution or a Poisson distribution. So when you have an underlying distribution, you will be able to predict the probability of each of the point. It's a continuous distribution. So if you take about each of the point, you can calculate the probability and you can use that probability to predict. This is a Bayesian distribution. Now, frequency based guys will tell you, oh man, you are wrong. You are not looking into data. You are saying about your previous experience. I don't care. When you put more data to it, what central limit theorem tells, you put more distribution here. So something like that. So this is a distribution. This is an actual distribution. So you have data of 3 distributions. So it is now the distribution is looking like this. So you create a sample like that. The distribution with this. You create a sample. You create a sample. You create a sample. Then what will happen? This distribution will be this. After maybe 2000 trials. In the meanwhile, you put more. All right. So this distributions are equal. So with more data, Bayesian and frequency distribution matches. This is a concept of Markov's model. This is a concept of Monte Carlo. Monte Carlo find out the expected value, expected probability based on sampling. It will start with if you just see 3 observations that you have put in, it will able to predict the probability based on the distribution. And it will say about the probability, it say about the reward function, everything. So this is a model based. You don't have the data and in a complex environment, you cannot put, because you do not know the interactions, right? You do not know the transition probability. The Monte Carlo will do it for you based on sampling, based on some trial data. So you train the robot 3 days and put it into Monte Carlo. Monte Carlo will create a simulations for you. You don't have to train it every day, and it is able to predict the probability. And it will able to predict. So when you predict the probability, you know so you have to pass on the reward. So everything is there only for 3 observations. ST is there, ST plus 1 is there. Your transition probability is not there, right? You will have rewards, right? Each of the state you have rewards. You pass this value to the Monte Carlo. So Monte Carlo will do is that it will create a table for you. So it will create what? ST, st plus 1 transition probability for each of the state, and it will, from this rewards, it knows for each of the transition probability what will be the reward. So this is the actual thing, that is the difference between a policy or the like value or policy based and a model based. Model based doesn't have that probability, transition probability. It finds the transition probability. Clear? Okay. So what we saw about value based is goal optimization is to optimize the value function. Okay, so it informs the maximum future rewards, and so future rewards we are able to predict, and from that value you are able to know that which is, so you from this thing, see, intuitively we understand. From here we see this is the value. Okay, so right now what we say is that so for example, this is the path again. So you add the rewards. I am not using a discounted factor. I total reward from this is preferably 10. You have the value here. So you take this path and find out the rewards. Okay. Once I am saying from this state to goal, there can be start to goal. There can be thousands of ways. Okay. Thousands of ways. So it will start from S1 to S2 to ultimately S8. Value is total rewards. Value is nothing but a sum total of rewards. Reward is 0.8. You take S1 and then S2. Instead of having S3, you move up here, S4. So now the reward is 0.9. Then S1, S8 and S9, the reward is 0.6. Now you select the path that has a highest reward. Okay. So I am not taking discounted. So means all the steps are of equal importance. And maybe if you want the later step to be more important, you can add a discount factor. So this is a value. So from value, I can find out the policy. Then for each of the grid world, so if the grid is around thousands of squares, so each of the value you have to do, and then it will take a long time. This is a value based. So from that value, I found out the optimal policy. Okay. So provides a distribution of probabilities all over stochastic. Stochastic, we saw it. What is our transition probability? So I'm not going into this policy. So I am saying you can find out the value from the value. We'll see it in next class. From the value, we calculate the probability, or calculate the policy, or you can calculate the policy directly. Same thing. Okay. So policy based is that from value, you know the policy. Here we are saying directly the policies. So you are not calculating the value. So you know that I take right. So right, left, right, left, you have a value function. You have a total, like the value is 0.7. Here we take a left and then left, right, left, 0.2. So you say this is a best policy. This is quicker. Why? Because we are directly calculating the policy value. There we are calculating the value of each state and then checking all the values to find out the policy. But here what we are doing, we directly find out the policy itself. Right? So this is a difference between the two. Hope it is clear. People don't understand. Hope it is clear. Now this action critic method I will not explain. So we will take it in the next class. Okay. So just here is model based and model free. So here we say about model, focus on the model, but there can be model free also. So model free means I am again the same confirmations. A model based is more on what you are doing. So each environment, each state and all. So model free is something that we will see is that it doesn't know about the environment, because in order to know the environment, it will be very tough to understand. So we will ignore the environment and we will do the sampling to find out the transition probabilities. Okay, so it is model free, means it doesn't care about the environment, like a Monte Carlo. Okay, model free RL means it doesn't care about what is the underlying distribution. It will or underlying rules. So for complicated thing, we will use a model free rather than a model based. Okay, that is a thing. And episodic task and continuous task, we know episodic task is some task that has a goal. Again, the same thing. So, sorry, you have a like this one, you have a goal. So you're moving from 1, 2, 3, 4. This is episodic because you have a goal. You know the goal. For example, there is no goal. Which type of task? Share markets. I have to optimize the share market. That is a goal, but there is no end state, right? It can be anything. Okay, it can continue forever. All right. There is no optimal. So what do you mean by optimal? So it depends on you. Maybe earning 1,000 rupees is my goal. Your goal can be earning 1 lakh of rupees in the share market, right? So this is continuous. So tomorrow, I will think tomorrow, there is no end, right? Because tomorrow my market can be bigger than today only. So it can continue forever. So this is a continuous task. An episodic task is preferably training a robot from point 1 to point B, or training a chess game. So this is an episodic task. Episodic task means what is divided into episodes. And continuous task is there is no goal at all. So it's a continuous. Okay, so this is a continuous task. Okay, so now we have covered this part, and exploration and exploitation is we have covered, right? Same thing. Exploration and exploitation is one of the, I will cover this tomorrow. Okay, exploration, exploitation.